So we are doing I/O virtualization on the other track, the non-assignment track, and I'm going to try to wrap this up today and introduce a couple of new primitives that are because of virtualization. Right. So let me try to get this discussion going. So first design we were really talking about is the I/O full virtualization support for I/O. And this was primarily through device emulation, right, and more specifically ISA, or not ISA, let's say device interface emulation, right. So the guest driver programmed for a virtual device, and if the virtual device was said to be one of the physical devices, you had to emulate the entire interface of that physical device and do whatever it did. And we, I think, drew a big picture about the different layers that were involved in trying to set up this emulation correctly, right. And a couple of we left the discussion at a couple of points where we said why this is correct but might be more complicated from an efficiency perspective. One was that the complete set of interfaces have to be embedded within the hypervisor for the hypervisor to make sense of what these interfaces are. And as interfaces keep changing and devices get upgraded, all of this has to be continuously evolving within the hypervisor framework to keep the one-to-one mapping between the virtualization abstraction and what the guest is trying to use. And the other was like full virtualization, which provides this unmodified guest. There is a lot of trap and emulate kind of situation that needs to happen for every instruction that goes through. And if your ISA is a very broad ISA or many, so for example, the example that we were looking at last time, there are 3 registers which we want to do I/O on to write or read from disk. Every write to the register is a trap, because we are now virtualizing this register to say, here's a register for you, and if you write to it, you are actually writing to a disk register, right, but there is no disk register that is actually exposed. So every write to that register has to be trapped, right, and there is a lot of complexity of emulation and overheads of emulation, right. So you have to keep trapping. So if the device interface has 10 registers, then every write is a trap of 10 writes essentially before you can actually understand what that whole instruction is to communicate with the device, right. So there is a full virtualization has this nice equivalence property. So guests are unmodified but has a bigger cost to pay in terms of correctness and performance, right, and that plays out the heaviest in the terms of I/O, right. So the other design that we are really trying to look at is what's called the PV approach, and this has been the story of all our designs so far, right. So this has been a story, and the PV approach is what's basically called the split device model, right, or the split I/O model, right. And here the design philosophy is simple, saying that because the guest already knows that we are virtualized, we are going to extend this this framework to all devices, and then we know that these virtual devices may not be the actual devices anyway, right. So in fact, we've also seen that you may have a virtual device in the VM which is a disk, but the actual emulation may be through a file, right. So there are all kinds of things happening. You have the disk abstraction exists, but at the back end all other kinds of things may be happening, right. So for you to be able to do a whole bunch of device processing in the guest may be unnecessary or may just be a complete overhead, because eventually the physical disk is going through some other stack, or the physical device is going through some other interface and other stack, right. So the philosophy of the para-virtualized approach is to have a simplified device, right. We don't have to do IP checksum calculation or TCP handshake, or go through an encrypted disk system and a decrypted disk system probably, or have a very sophisticated interface for a disk, because we know at the end of the day we will pass all of this information, but the hypervisor is anyway going to do whatever it has to do with the actual disk, right. So we will simplify the interface. The idea is to simplify the virtualization interface to make it more amenable for the hypervisor to quickly process your I/O. Right? That's the deal. Yes.
Basically, we are simplifying on the guest side.
The guest side. Yes. So the virtual devices interface to which the guest driver programs to is now becoming a very simplified interface. Right. So sorry. Go ahead.
As the hypervisor is anyways doing the business of
Actual communication with the device, right? So in fact, the main task for us from a guest perspective is to make sure that we hand over the data to the hypervisor, or the hypervisor hands over the data to us in whatever is the semantics of the device, right? So if you are reading from a disk and you specify a block number, all you really care about is what is the content of that block, right? You don't really want, you are okay, you're okay if we don't do the device emulation, as long as you know that block 23 was written something, and if you try to reattempt and read block 23, you get the same contents, right? So the primary task of the PV hypervisor is to read data correctly from the hypervisor and pass data to the hypervisor correctly, not necessarily through a device interface. It could be any interface, right? And it's a virtual device interface, so we're just going to make the interface of it very, very simplified. So what do you think is a possibility of setting up this channel or this interface, or the mechanism to set this interface?
The virtual hardware machine that we have studied last time. So we will write to a memory location, and then IOCTL exits, and the exit status of the IOCTL will tell that hypervisor has to read from that memory location. It will read it and do IO stuff, and then again show everything gone.
Well, so the IOCTL is still restricted within a application and a guest, right? So now we want to move between a guest and a hypervisor, right? So the current primary interface between the guest and the hypervisor is basically the CPU registers, right? There are nothing other than CPU registers that can be used to do any kind of communication between the guest and the hypervisor, right? Or a trap mechanism, right? So now if you want to pass data, so now what we are trying to do right now in the conventional world is you try to write to a register, the register gets trapped, and the hypervisor interprets the write on the register to do something, right? So for example, if you write 0, it's saying, oh, now you want to read. The next register you write a number, it's saying, okay, this is the buffer where the data needs to get copied, right? And then it will do some action eventually and emulate that instruction, right? So if you say 23.0.1000, that means you want to read block number 23 and copy its contents into pseudo physical address 1000, right? But the virtualization engine can then do anything, get the data and dump it in PPA 1000 eventually, right? But the interface of communication is basically just a bunch of registers, right? But we can do much better with PV. Right? And what do you think can be the channel of communication?
He doesn't make it shared area.
Sorry?
He doesn't make it shared area.
Right. So because the hypervisor and the guest are operating on the same machine, now you can actually just make use of a large chunk of memory to say this shared memory region is where all the channel of control and data will pass through. Right? So you can write to a memory location as a guest, and the hypervisor can read the same memory location and interpret it to say, oh, this is basically happening, this is a read operation. And now instead of writing one byte at a time, you can write the whole tuple 23.0 and the address in that memory location, and then tell the hypervisor I am ready with my request. Or you can list 10 such requests in that memory location and say I am ready with my request. Then the hypervisor can read all of them because it's just a memory read, you don't have to do a trap. And then you can interpret all those reads and then do whatever you need to do.
Right? When you are saying hypervisor, you are mentioning to the OS level program or the user level hypervisor?
That will come about. We can do it both ways.
Currently you are referring to?
I'm like waving my hand. But yeah, it's done in user land, right? In most common implementation, it's done in user land. So let me draw a picture. I think I've said many things already, but let me try to draw a picture for this. So this was basically pioneered by Zen. There's also a standardized virtualized interface for virtual devices now, which is available by default in Linux, called virt.io, which is basically virtualized IO, para-virtualized IO for virtual machines, and it's an open standard and specification to build new virtual devices if you want to, using this idea of PV. Linux already has support for virt.io net, virt.io block, virt.io PCI, and a whole bunch of other virt.io devices which use this model for communication via shared memory channel between guests and VMs. So let me draw this picture. So I'm going to draw this picture which is also relevant to virt.io, but this was really from the Zen model, right? So let me draw this picture first. So what does the PV approach or the split driver approach do? It has a simplified and standardized device interface for VMs. Guest OS, or in fact the driver drives the simplified interface, right? So such a device may not be physically available, so this driver will not work on a bare metal machine, right? And of course VMM worries about actual device interface, right? And it is split because there is a virtual and an actual device interface. Right, so let me try to draw a picture for this. So this is Zen. Okay. Okay, so this is some representation. Let's see. So this is Zen's representation of how virtualization looks. So Zen already has a user level component and a hypervisor component. So the way Zen works is it's like a hosted OS almost, but also is full virtualized, in the sense the only hypervisor that runs on hardware is Zen's hypervisor, but it also has a user space program or a control environment called DOM0, which you can boot up into and start new VMs and things like that, right? But the purpose of that DOM0 is really just to control the VM environment of other VMs, but it's a user space environment, right? So there is a full-fledged guest OS here, and so this can be, so backend can be in the guest OS as well, or can be in the user space of DOM0, the control domain. Right, so this is similar to QEMU, where QEMU is a process which is trying to set up a hypervisor. But in Linux, QEMU the process and QEMU the VM are integrated as a single process which run as different threads, whereas in the Zen model, there are different entities sandboxed in different VMs, right? So the controller itself is a VM. And the idea is as follows, that whenever a new VM comes up, it basically registers itself with the control plane, or whenever the new VM comes up, the control plane is the one which basically starts the VM and registers a bunch of shared memory regions for devices that have been exported and probed by the guest, right? So for example, when a machine comes up, it probes a bunch of devices. These devices are exposed via some Zen protocol which says you have a bunch of these devices. So for every device that you discover, you need to start a device driver for it, and then the device driver sends a bunch of initialization commands to initialize that device. And as part of that initialization, a bunch of information is exchanged between the hypervisor and the guest, which essentially is trying to set up these two shared regions. One is a control channel and one is a data channel, right? And now all I/O is basically happening on these channels, right? So for example, if you want to do a read from a disk, all you have to do is to park a descriptor here. This descriptor basically points to some region. It has an address of this region, right? And it says that I am a read request and I want to read block number 23. And that is then interpreted by the backend, which is actually doing the virtualization, and the backend goes through the actual driver, like we have seen before, to read from the device or however the disk is actually getting emulated, and then copies the contents of whatever was supposed to be on block number 23 into this shared memory region, and then sends a reply back on the control channel saying the read is done. So whenever the guest gets scheduled next, this control channel or this event channel is probed for some interrupt kind of a mechanism or a software interrupt kind of mechanism, and the guest knows that this read has happened, and then it will read from shared memory, right? So the point being that the interface between all of these entities now is really shared memory transfer, right? Not register write, register trap, and register emulate, right? Yeah, sorry, there was a question.
Sir, about this IO ring, where is it stored? Like it is hardware support?
No, so this is memory. This is in memory. So this is all a pure software solution. There is no hardware involved in this.
Shared data region is also a part of the memory.
Part of the memory, yes.
In memory, so the shared data region is shared by all the guests here.
So this is all in memory. So this is all in memory. In memory and shared between the hypervisor and the guest.
The IO ring is also shared among all the guest OSs and the reading.
No, yeah. But the deal is, in this case, so there is a per virtual device IO ring, or it depends on the device, right? So for example, for the network there is what's called a TX ring and an RX ring. So there are two rings per network device, whereas for the block usually there is just a single ring for either saying read and read done, or write and write done, right? So it depends on the type of the device.
But these rings are like one common ring is shared among all the.
No, it's per device, per virtual device. So if you expose a device to a guest, that device gets a ring for communication with that virtual device on that VM, right? So if there is another VM which also has a disk, that virtual disk that the hypervisor is going to emulate now will have its own IO ring, because you can't have events for one VM being transmitted to events on the other VM, right?
And so this particular memory region should be always be allocated into a physical memory space.
Yeah. So this will follow all the standard memory virtualization and memory mapping requirements that are needed.
No, so like in the virtual memory, we said like malloc is done, but we don't actually allocate in physical memory.
Well, that's just the scam, right? Doesn't matter. Once we say you have valid virtual memory and you access it, that valid virtual memory will get resolved either way. If it's already pre-mapped, the access will go through. If it's not, a page fault will occur and someone has to handle the page fault. So the page fault can be for many reasons, right? You decided to take the machine for a spin and started accessing random virtual addresses. And you may hit a virtual address that you have not allocated or declared that you are going to use, and that's like a page fault that can cause undeterministic behavior. Whereas you had done a malloc and then you accessed, then that's a valid access. If there is no mapping, then a page fault has to handle the mapping, create the mapping, allocate the page, and let the access go after that. Right? So those are two different. That abstraction is always when you say I do virtual memory, that abstraction is automatically available.
So we inform the DOM 0 that something has been written to the shared memory.
Something has been.
After writing the data into the shared memory, how we inform the DOM 0 that I have written something and now you have to inform it.
So there are ways to do it. The most basic way to. So the point is how do any of these entities know that there is something in that IO ring, right? So there are different ways to deal with it. The simplest of which is to have a polling agent. So whenever DOM0 gets scheduled, because DOM0 is like any other VM, the hypervisor has to schedule it. So whenever DOM0 gets scheduled, one of the tasks or one of its main tasks is to understand the status of these channels. So it will probe them, right? And the same in the guest, right? So whenever the soft IRQ or the soft device driver threads are scheduled inside the VM, they will be polling these event channels. So it is like any standard eventing mechanism, right? So event shows up, you have to understand when the event came in, right? So in fact, you can kick in that process by setting the CPU state to have an interrupt. But the interrupt handler is not actually going to jump and look into an interrupt. It's going to look at all these channels to understand what's there in the channels. So let me just write some items here. Right?
The polling has to be done by the VM.
The polling has to be done by DOM0 to understand whether the DOM0 has any pending events that it has to process. Simultaneously, polling has to be done also by the guest driver. In this case, it's called the front end, to see if there are any pending events that the guest has to process. Right? So if you issued a write command, you need to know that the write is over to read that information back. Right?
How is the communication between the hypervisor and DOM0 to equivalents of hypervisors?
Yeah. So that is shared memory. So you just write to it. So the IO ring and the shared block is just shared memory. Both the entities DOM0 and DOMU have mapped virtual addresses in their regions so that they can directly just write to them.
Yeah, but the VMM can also access the shared memory region.
It could, but it has no reason to. It is only setting up that shared region.
Yeah. So it is getting information from DOM0 through hyper.
Yes. So the setting up these IO rings, and sharing them across VMs has to happen through a hypercall. So that DOM0 can't do. So DOM0 can just say, I'm talking to a VM and I want to set up an IO ring. I make a hypercall to do it, right? The hypercall will set up the rings and maybe pass a descriptor or a reference to it. And the guest will also do the same, saying, I'm also trying to set up this virtual device. And then the hypervisor knows that these are the same two ends of the same device, right? So it will mark this shared memory in both these.
The polling that is happening is through hypercall.
No. Once the shared memory is set up, right? So for example, DOM0 and DOMU, suppose there's a new device and we call this, a new device, let's say it's a virtual device of nature block, right? And it has some block ID or device ID, some device ID, right? So this is basically trying to emulate a disk. So there is going to be a hypercall from DOM 0 which says something like set up virtual device state for whatever device ID some number ABCD, device type block, right? And that's a hypercall that DOM 0 is going to make. So on this hypercall, what will happen is that the VMM sets up memory region for IO ring and shared data region. Right? And this is mapped into the DOM 0. So now DOM 0, whatever read or write access it can do, does its own memory space is being mapped into the region that the hypervisor reserved for it. Right? So similarly, if the virtual machine also does something like a initialize device ID, and that's also a hypercall. The VMM looks up config state for this device ID and maps shared regions into the VM. So now the VM also has a mapping for the same shared memory region. Once this setup is over, the hypervisor really has no role to play.
DOM 0 is also a VM.
DOM 0 is also a VM, yes.
If DOM 0 is also a VM, then when it has to do IO operation, actual IO operation, then it has to go through that.
So that's this picture. The DOM 0 eventually, so that backend is the emulator, right? So if you are doing a disk, you may want to read actually from a file, right? So that logic is stuck in what's called the backend, right? Because the backend is the emulator of the virtual device. Now when you decide to read from a file for a disk that you have emulated, the file has to still be read, right? So you'll make some fread call or a read call that will eventually go through a system call, that will eventually go through a device driver, and that device driver can talk directly to the physical interface.
DOM 0
is a privileged virtual machine. Yeah, it's a privileged virtual machine. Right, so the actual driver that will talk to the actual physical device is residing in DOM 0.
So basically you're trying to say that any DOM other than DOM 0 for accessing a device, it will have to just go for one initial hypercall, which is to set up the shared memory region.
Right.
After that, it only has to write to the shared memory region.
Yes. So all the device interaction interface is now in shared memory space. So if you want to do read, you will actually write a descriptor in that ring saying I want to read. So there's a standard structure that you can follow, like we had said, right? There's a 3-register structure for a device interface. So you can think of that as a 3-register, 3-variable structure, and that structure can just be written into this descriptor. So there's a format, of course, for these descriptors, but assuming that descriptor is like what we were doing with our 3-register disk, so it can be 3 variables. The first variable says which block you want to read, the second variable says whether you want to read or write, and the third variable is an address in this shared memory region where you want that data to show up. And you make this structure and you just dump it into this IO ring, right, which can be a queue or a linked list or whatever, it doesn't matter. And then at some point DOM 0 is going to get scheduled, and DOM 0 is going to read that descriptor list to say, okay, are there any pending descriptors that I need to deal with? And it will see a descriptor which says, oh, this has not been dealt with yet. It will read it, it will have 230 some address, and then say, oh, this is device ID 4645, which is basically a block device, but I am actually trying to fake it via a file, and they are trying to read block 23. So block 23 is actually offset 445 on the file. So let me read offset 455 on this file, 512 bytes, and will issue that read, right? And that read will go through its own IO stack, file system, device driver, etc., etc., and it will eventually get those 512 bytes, and it will copy those 512 bytes in the shared region that the RX descriptor had told it to. And once that copy is done, it will maybe flip a bit in the structure to say read finished, right? And whenever the guest is scheduled next, it's going to try and poll the state of its read, and it will say, oh, the read is complete. So it's as if the device came back from a physical read, but it's not. The physical read happened somewhere else. Now we are just using the same idea but on a different channel to say the read is complete. Yeah.
Shared data region is per device or per device per VM?
Per device per VM. I mean, again, that's an implementation. I mean, you can have one large shared memory as long as you don't mess up each other's shared memory, you will ensure correctness. But usually the hypervisor will try to implement it on a per device per VM basis.
So
Yeah.
DOM 0 is per VM setup.
No, DOM 0 is a special VM that Zen boots up into, and it's like a dashboard, right? Through which you can start all the other VMs.
Like it's an extension of the VM itself.
Sorry?
It's an extension of the VM itself.
Extension.
VMM.
It's an extension of the hypervisor, yes.
Why is it a VM? Like, why is it not just a why is it not part of the VMM? Why it should be a VM in the concept of a privileged VM?
So, because, so the question is, why should DOM 0 be a VM, or why this model? I mean, one of the answers is that the Zen is a hypervisor, a bare metal hypervisor. So Zen sits on top of bare metal, and it's ready to create VMs. Now, how do we create a VM? There has to be some user space component, right? Like an operating system sitting on a bare metal is dead weight unless we are in user space, or you have a shell program to create other programs. So similarly, we need some interface to have access to the hypervisor.
So similar to init program.
Something like that, right? But this is slightly more heavier than that, because we could have had a init program which runs the hypervisor, right? If you want to. But then the point would have been that the hypervisor is also acting like a traditional OS and all the other OS things that it has to do. So they have just basically said, the hypervisor remains to do only hypervisor things, which means, do memory virtualization, do CPU virtualization, handle hypercalls, and schedule VMs. It doesn't want to schedule processes, it wants to schedule VMs. So now with that abstraction, everything on top of that has to be a VM, right? And that's why the dashboard VM, or the privileged operating framework, is also through a VM.
So how does the VMM manage when means the scheduling of this DOM 0 and the other?
So it's just like any other VM, right? So there are many VMs running and being supported. It will just schedule any of them according to some scheduling policy.
Only the guests means there can be chances that only the guests are getting scheduled. The DOM 0 is not getting scheduled. So all the guest VMs are.
Yeah. So that is how intelligently you design the scheduling policy, right? So for example, if the guest has written something on this IO channel, right, then it's much better to schedule the DOM 0 next, because otherwise, no one is consuming the channel.
But if some other VM guest OS gets up, then that won't be processed.
That won't be processed for the first VM, yeah. So if everyone is just parking items in that ring and progress is not happening, then it's just a bad scheduling policy. Yes?
Initially, like in the pre-virtualization, what was happening is like there were virtual block numbers being guest OS.
Yes.
Then the device emulator we used to translate them into physical.
Correct.
So here that like this guest OS block process, this VM is not like sending any virtual block or something.
No, everything is the same. It's all virtual. It's just that in the last case, that virtual block number 23 was not known to the VM that it's a virtual block. It was thinking, hey, I'm talking to a disk. The disk has 3 registers. Let me write the block number that I want. it's still going to do the same thing, but it now knows that it's not an actual device, there's no actual registers. So instead of writing 23, 0 and an address on 3 different registers, it will pack them, say, in a structure which I am calling an IO ring descriptor, and copy that structure or that descriptor into this IO ring, which is equivalent of saying I want to read the device at block number 23.
Okay, and those IO stack checking and all those things won't happen.
Right. So now, because you already know all of this, you don't need to do all this other business of going through the IO stack in the guest. So the guest's IO stack can be much more simplified.
Okay. And this DOM0 process, since it has an emulator inside, so it will translate them all into physical address.
Right. So this box, yeah. So this box, right? This box is the same as this box. It can do whatever it wants. So it can say you are asking for, so only the interface has changed, right? So emulator is still saying, oh, you want block 23, okay, but I'm going to fetch it from Charni Road. Doesn't matter, right? So that emulation layer still exists.
And again, we will be using IOCTL and all to communicate just as we were doing here.
Yeah. So this channel from below can be anything, right? As I said. So if it is a network, then you have to actually open a socket, send a message on the network. Someone on the other side of the world is going to say, okay, this guy is actually requesting some data on this offset, and they'll funnel it back on the network. And whatever data comes back, you're going to attach it and say this is what belongs to block 23. So that emulation layer is the same, doesn't matter what it is. So it could be a file, it could be another disk, it could be a local disk at a different offset, it could be a network disk, it could be anything.
Because here also the emulator was basically another user process. But in this case, it's in the VM.
Yes, but it could be in the user space of the VM.
User space.
It doesn't matter. So the emulation can happen in this case, in full virtualization, in the hypervisor as well, no problem. Or in DOM0's case, it can happen in the guest OS as well, no problem. But the problem is, if you really want to change or keep flexibility of how devices can be emulated, every time you want to change the emulation abstraction, you will have to go into the guest OS and recompile it, or write a new kernel module and make sure that it gets attached to it. But if you are in user space, then it's much easier to fudge around with the emulation backend. So usually most of the emulation is pushed into user space, right? And I think that was the question that somebody was asking earlier as well. Where does the device emulation happen, right? So most of today's device emulation is being handled in user space, but that's no different from handling it in the hypervisor. Doesn't matter. In fact, there are some solutions which are saying that doing all this communication between this flexibility of doing or upgrading emulation, which is easier in user space, comes at a performance cost. So if you are all clear about how it's going to do, let's just bury it back into the kernel. Right?
And obviously there should be some sort of IOCTL call, so that, because obviously user process can't have the physical virtual, but without having any interface with IOCTL.
Yes. So IOCTL is one way to do it, but so for example, if you are okay, let me just write this again. Right, so if you are so if in the guest program you will do something like this: read file descriptor, buff, and some size. Right, so this is in the process. Right, so the process is going to make this call. Right, eventually there is going to be some syscall which will end up in a file system handling code, which will look up things like, it will look up the inode for this file descriptor, then it will look up the offset, blah blah blah, and then eventually it will try to make a call via the device driver, right, which looks like what we are trying to do: block number, read or write, and some memory address. Right? In full virtualization, this is a write to a register. This is also a write to a register. This is also a write to a register, and it's going to lead at least to 3 traps. Whereas in the PV approach, this can be a single copy to a ring descriptor. So this is what's called the control channel. This is describing what you want to do, not how you will do it. This is just saying what you want to do. I want to read something. So the interface of sending this information has changed between full and PV. That's all happening. Right? After this, what's going to happen is completely different, right? So for example, this 23, 0, some address can be emulated as I said, 2023, 0, some different address. So this is address X, this is address Y, and then converted back into 23. Basically, do this. Right? So this is the emulation. So this is the emulation interface. So this is all in the VMM space. Right. So the VMM may say you are wanting to read 23, but I will just offset it because I have given you different space on actual disk. Right, and I will copy it in my memory, then I will copy it back into your memory or something like that. Right. So you might have different address. So that might be how the emulation happens.
So this transmission is done by the DOM 0 in case of para-virtualization.
In case of para-virtualization, so this is in case of DOM 0, the emulation layer is, in case of para-virtualization, the emulation is sitting in DOM 0. Yes. Or it can say, I am actually trying to emulate your disk as a file, so I'll change this 23.0 to another read with a different file descriptor that I am maintaining for your device, some file descriptor for Y, and I'm going to calculate a new offset Y, and I'm going to try and read it at my address Y. Right? So that's the second possibility of how we are emulating the virtual disk.
So the first one is the full virtualization, second is the para-virtualization.
No, this is just emulation. This is not para or full. This is emulation. Para and full are not doing the emulation. It's not the emulation difference. The para and full IO virtualization is how are you passing the control and data information back and forth. How are you emulating the device to get the data is standard emulation. Right? Doesn't matter. So that can be any of these options. So it can just be a block offset, or it could be a file read, or it could be a network read. Right? So for example, you may have a virtual device with 4 GB storage, but the emulation might be such that 2 GB is stored on machine 1 and 2 GB is stored on machine 2, right? And the emulator is sitting right in between here. So based on what do you want to read on the disk, on the virtual disk, you may actually read data from this machine or that machine, right? And that is just your emulation technique that you are using. That has nothing to do with para or full. Right? Para or full is just saying how do you get this information about what to do. Do you get it through a machine interface, or do you get it through this ring interface or the shared memory interface. And because we are doing shared memory, we can do very nice things like send the control information in one copy, or you can batch all of these together and write multiple descriptors in one go. Right? Whereas in the full virtualization world, every write is a trap. Right? So if you want to write 10 descriptors, you are like trapping the VMM 10 into 4 times, 40 times, and every trap is a context switch, a trap handler, a virtualization on that. Right? So the overhead of going do that for IO is exceptionally higher, and that adds up because IO is inherently slow. right? IO is inherently slow. So the PV axis or the PV domain is most beneficial when you are doing IO, right? Because the other virtualization or the hardware support of virtualization actually caught up to say, you know, we can efficiently do, as long as you are not exiting for every instruction that you execute on the CPU, for most of the time your CPU can just conveniently and safely run guest code. Only once in a while when you want to do some sensitive stuff, you can exit, and that exit can either be through a hypercall or through a VTX switch, so it doesn't matter. So that cost of, you know, going between hypervisor and the guest can be smoothened out to a large extent via hardware, right? If your guest is not doing these switches all the time. But in the case of IO, there are the complications of emulating devices and device interfaces being all sensitive, right? There's no code in the device driver which is not sensitive, because everything that the device wants to interface with is a physical device. So you can't say, oh, work on this device for some time, then I'll come back and check whether you're doing the right things. You can't do that. You can do that for the CPU, because the CPU has a program, and as long as the program is adding two numbers, the hypervisor doesn't need to know that. Right? So you can hand over the CPU to the guest. You can't hand over a device to the guest. Right? So the PV approach is really the touchstone for handling IO virtualization with VMs. Right? So most of the commercial or the enterprise VM setups or even non-enterprise VM setups are really using this virtualized form of IO. Where even on your desktop, if you do IO in the conventional way, you know, you will see that your VM is just going too slow whenever you are doing read or write or network. Right? So even with desktop VMs, most of our options today are basically running VirtIO, right, or virtualized device interfaces. And thankfully, Linux has burnt it into its core kernel. So now, if you like device search, like Linux searches for devices, if it's inside a VM, it will actually see a virtual device, and then it gets attached to a VirtIO based driver, which is essentially doing this kind of a device transfer of control and data for virtual devices. Okay. So let me draw another picture. I'm just.
So what is the purpose of the VirtIO? Is it the one that is giving the hypercalls to create those links while the device is up?
Yeah. So VirtIO is a very broad term, and I think the equivalent of VirtIO is really split IO model. Right. So one instance of this split IO framework was developed in Linux, and that was called VirtIO. So VirtIO has a whole bunch of things. So it is a set of APIs essentially, which are used to do all of these actions, to set up devices, to set up IO rings, to register devices, to expose virtual devices. So that's the definition of that standard is called VirtIO, but it's actually defined through what's called a VirtIO API. So if you want to support a virtual device, you'll have to implement a backend and you'll have to implement a front end. So the front end has to recognize that virtual device, and the backend has to support that virtual device. Right? But all the communication that needs to happen through them can happen through what's called the VirtIO API. Right? So the description of that device and the registration of that device is a VirtIO API call. Initialization and registration from the front end side is another VirtIO API call.
Like a format was set up.
Yeah, so it's a specification, and then people have to implement virtual devices for that specification. Yeah. And that was also needed to decouple who is building the back end, who is building the front end, because front ends are in guest OSs and in VMs. So the Linux approach was, if you can standardize the virtual device specification format, then we can write device drivers to that specification, right? So that's how. Sorry.
Since the memory is shared, I mean, there's a are there any security vulnerabilities?
Security vulnerabilities. Yeah. So security is always a big boo-boo. It's not clear how it will play out. But here the security or the fault domain is or what is I think it's called the attack interface. My lingo about security might be very poor, but I think what's the attack interface, right, for the VM to get compromised? Right, so whose security are we, first question is whose security are we worried about, right? Is it the application, is it the VM, or is it the hypervisor, right? So there are several entities that we are worried about. For now, we don't worry about the hypervisor. The security of the VM has something I think called the attack interface, which if compromised, if that interface is compromised, then the VM can get compromised, right? And I think in these cases, the attack interface is really the hypervisor or the hypercall interface or the trap and emulate interface. So whatever abstraction or the interface that the VMM is providing to the VM, if that cannot be trusted, then of course the VM is compromised.
Basically sharing the shared data region is going maintained
through the hypercall and trust on the hypervisor. If the hypervisor itself is doing hanky-panky stuff, right, then all bets are off.
One basic doubt I think if you are doing hypercalls here, earlier we were trapping. So how are they like here also there is a high overhead because of it?
Yes, but a hypercall is a programmatic invocation. So you can say I am making a hypercall. What you need to do in this hypercall is described in this structure somewhere here. So read that structure, and that structure itself may have a list of 10 commands. Each of them would have needed a trap and emulate in a full virtualization case. Right? So we are basically just saving on the overheads of how information is communicated back and forth through a para-virtualized approach. The information itself may not change.
Because the overhead is like much higher compared to like the trap and everything.
Yes. So that's why. So there is no register, unfortunately, which says, I am pointing to some sensitive information, but that's really a big collection of sensitive information. I am going to do a single write, you go and read that. That's not part of the conventional ISA. Right? There are very few such registers, like the IDT register, for example, which points to an IDT table. But if you want to update some information, you are going to do it one register at a time. Right? And every register write becomes a trap. Whereas with para-virtualization, you can try to amortize that cost by really saying chunks of, you can pack descriptors together for a single request, or you can batch a whole bunch of requests, right? So for example, in network IO, you can say, I don't want to send every packet, I'll send packets, 10 packets at a time, or I will only read 10 packets in one go. I don't need to disturb the IO processing thread to handle one request at a time. Can't do like that in full virtualization easily, right? Because every time a request comes, you're going to get interrupted. Yeah.
So usually in virtual devices, we see that the VM shows that we have a virtual device interface, like a virtual bit 0, 1, 0. So the VM, so these devices don't show up as traditional ETH0 or some other interfaces.
Yeah.
So the device drivers for if I have a specific device driver that works for just like ETH star devices.
Yeah.
So it won't be interacting with this.
Yeah.
It won't.
No. So if you have, there's a network interface card called E1000, for example, right? And there is a driver for that E1000 device, because E1000 has a very specific interface and a specific language if you want to talk to that E1000 type device. On the bare metal world, if you have a driver for E9000, it will not work for E1000, right? Because the interface has changed, right? And that's the problem. Every time a new device comes in the market, they have to have a driver to talk to that device. So if you change the generation of a network interface card, if you are lucky, the driver may be back compatible and it may work. But most likely you will need an upgrade to the driver because now the hardware interface has changed or the sequence of messages have changed. Similarly, if you expose a virtualized E1000 driver, now you are the virtualized E1000 device, then you have a driver which is talking to that virtual interface. So that virtualized interface driver will not work with your physical interface. Right? So each driver has to talk the interface that the device understands. So now in this para-virtualized case, if you change the virtual interface completely, you will still have a driver, of course. The front end is still the driver, but it's talking to the virtual interface. So that will not work on your actual, this device. This device needs a driver which knows this, needs to know how to talk to this device.
We can just for a virtual use, you can just get rid of those drivers and just
Yes, yes. I mean, unless the drivers have been written in a manner with some hash defined which says if you are going here do this, if you are going here do that within code, you can get rid of those drivers. Yes.
So, what do we exactly mean by guest driver there? Like,
This one? So this guest driver is talking to this guest. So I should. That's a very messy figure. Sorry for the. So this is really the. If you want to really label it, the virtual device. Right. So the virtual device needs a driver, right? So now, in the first case, when I wanted to write to the disk, I was actually or read from the disk. The driver would write those 3 registers. Now here, the driver will write to the channel.
How will Linux knows that device is virtual or it is actual?
So that's part of the device discovery. So whenever a machine comes up, it has to scan its PCI device list to see which devices are available. So in this case, when it's trying to do that, because you have a virtual device registered as part of your configuration, the PCI virtualization will feed you that information via the hypervisor to say that you have 3 devices. These are the device types.
These are virtual.
Yeah, and I think in this case it's much easier because we can add new information to say this is a physical or everything is a virtual device in this case anyway. So let me draw another picture. I'll just draw another picture maybe. So I'm going to try and draw the back end. The back end for some network I/O. Right. And let me try to see if I can. So this is the backend driver if you. Yeah, so same picture but a little bit zoomed in. So basically what it's saying is if you are doing network I/O at the back end, you will have many interfaces, right? And as someone was asking earlier, this is say VM1. If there's another interface, then you are basically connecting to another set of queues which are basically mapping to VM2, right? So but all the coordination in the management of this has to go through has to be funneled through the back end, right? So every packet that's coming in or every packet that's going out is really going on the physical interface that's controlled by DOM0, right? So the rest of the stuff is just in software. So right, so that switch is a software switch. So every packet, so in the network world what will have to happen is every packet that comes in will have to be processed by DOM0 For what? Why should every packet that has to be is received be processed by DOM0?
So because it has to understand like who had asked for that packet.
Yeah, so because it has to switch the packet to the appropriate VM. And how will it do that? What will it try to look for? Right, IP or a MAC address, right? Because all interfaces are eventually mapped to a MAC address, and maybe a higher abstraction if you are doing layer 3 processing to an IP address. Right, so based on which layer of the stack you are switching those packets on, the backend inside DOM0 will either will have to act as a layer 2 software switch or as a NAT box or a router, right? Because if you are doing layer 3 processing, you have to emulate some kind of a router. But if you are emulating layer 2 switching, you will have to operate like a software switch, which means you have to look at a MAC address, right? And a MAC address is a valid reference because you are exporting a network interface. So that network interface in the guest will anyway have a MAC address, right? And this will actually operate like a physical switch, but in software, because the physical switch is connected to a network interface card or a line which is connected to a network interface card which has a MAC address anyway, right? So this is just a emulated software switch if you are doing layer 2 stuff, right? Or if you are doing a layer 3 stuff, you act like a router essentially, or a NAT box.
So DOM0 content, which is like for network and for disk driver also it will be the same.
Yeah, so it will have to use some similar multiplexing technique for the disk as well. Yes. And that will be part of the emulation layer, right? So you will say virtual disk device for this VM is really this file. So if you are reading from this file, then you know which device to connect it to. Yeah, that's absolutely. So that mapping in the disk case is a different type of mapping. In the network case, you can ride on top of the MAC addresses and the IP addresses and implement a software switch or a router to do the equivalent, right? So you can't emulate network as, disk, because network endpoints are network endpoints for communication.
Disks won't have a MAC.
Yeah, so there is no equivalent abstraction for that. So there is one hitch in this picture though. So the only entity that's really talking to the physical interface is DOM0, right? And of course, so there is this physical interface has a MAC address as well, right? So do all these interfaces, right? So all these other interfaces that are connected to, so this has a MAC address as well, this has a MAC address as well. So all these virtual interfaces are also connected to MAC addresses, right? Or IP addresses, doesn't matter. Correctly MAC addresses, but you may switch on any of these, and packets that are coming on, but these are all different MAC addresses, right? So this might be MAC address 1, this might be MAC address 2, this might be MAC address 3. This interface for DOM0 to do IO itself may have another MAC address 4. So what's the problem here?
The outside outside other NACs are
Yeah, so to the outside world, all this doesn't exist. For the outside world, all that exists is this endpoint, right? Or the physical MAC, or the line that's coming from your, from your cluster or your router or your physical switch that's connected to your actual physical machine. So there is only one MAC address that the outside world knows, but the inside world has a whole bunch of other MAC addresses. I mean, a MAC address is a number, but it could be virtual. But the problem is, you really want this VM to talk to the outside world, right? So if you want the VM to actually be, so you can't say I am creating a VM, I am going to give you a MAC, it's really a virtual MAC, but it cannot be used to communicate with anybody else in the world, right? Or any other machine. That can be translated, but the point is now, unless you are the router which operates at layer 3, it can then receive all the packets from this physical interface, right? Because the router is like a layer 3 jumper. So this layer 2 MAC for the router will work, but then it means you have to implement processing up to layer 3. But you can also just implement processing at layer 2 if you want to work as a switch. But the problem is, if you are working as a switch, you need to get all the packets in, whereas only packets which are destined to this MAC address will actually physically be delivered into this machine. Right? So how do you receive a packet? Right? You receive a packet on a machine only if the MAC address of the of that packet on the line matches your MAC address. Right? Otherwise, that packet is not sucked into your machine. So now, if you are working at layer 2, you are only operating at MAC addresses, and you have a whole bunch of other MAC addresses inside, and those MAC addresses, even if they are on the wire, will never get sucked in because they won't match your physical MAC address. Right? That's the problem. But that is solved by, how do you solve that problem? So there is something called as a switch. There is a switch on the NIC which says I want to read all packets or I want to read my packets. Right? So there is something called as the promiscuous mode, which basically sucks up all the packets on the wire. So as long as the wire is only sending packets that are on your machine, it may not still be an overhead. Right? So generally this is an overhead because if you suck up a packet which doesn't belong to you, unless you are like a rogue operating system or a telemetry box which actually wants to look at all traffic, this is just spam, right? Where you are looking at packets that you are never going to process. Your IO stack is going to keep, every packet that doesn't match your description, the IO stack is just going to keep dropping them, saying this packet doesn't belong to you, this packet doesn't. So it's just work which is useless work. Right? So normal configurations will only turn off the promiscuous mode so that the MAC check happens in hardware and every packet that comes through the NIC belongs to you. Right? Whereas in promiscuous mode, you are basically disabling this check and every packet is coming in, which works for us in this purpose because then you can actually look at the MAC header and say, oh yeah, this MAC is actually my VM. Oh, this other MAC is my other VM. And then you can push them in the current virtual interfaces. Right? So this is really enabled only if enabled via what's called a promiscuous mode of the network interface. So for layer 2 switching. To get packets with all MAC addresses.
So I have a question.
Yes.
If there's a packet meant for some say VM1 which comes, so what would be the destination MAC in that packet?
It should be
MAC2.
MAC2. Yeah. Oh God. Oh yeah. Sure. Yes. So MAC2 for VM1. That's a bad thing, but yes. So let me just call this VM2 and VM3. Okay. Yeah. Yeah, so this is like any other machine, right? A machine sends a packet on the wire. The MAC address of the interface on which the packet is going out is the first address of that packet, which is the MAC address.
Sending the packet, then which MAC address?
If it's a layer 2 switch, it will, if this is a layer 2 switch.
When you're sending, you will put MAC2 in the packet.
MAC2 in the back. Yes.
And then the VM will have to have this logic within it that MAC2 is also a part of one of my virtual
Yes,
codes.
yes. Yeah, so that's stored in the backend, right? That's stored in the backend. When it initializes the device, it has to label it, and that label will be a MAC address. So it will say VIF0 is really MAC2. So if an incoming packet comes in which has MAC2 as its so destination address, it will put that packet onto the channel of MAC2.
Is it not cause any issue that you are sending a MAC address that is not yours at the NIC level?
It won't, because in promiscuous mode the network interface card is just now acting like a conduit. Everything that's coming in, everything that's going out is allowed.
Okay, so you were saying that this particular VM would look at every packet that's coming on the channel.
It will
If
happen.
it's among the set of MACs which it supports, then it.
Yes.
So every time we are using names, we are making the network slower.
Every time we are making VM, we are using VMs, we are making network IO slower. On that machine, yeah, you have to do more work. Yeah.
Mac 3 line, we have a Mac 3 line, right?
Yes.
So that line will only receive the packets which are destination for the Mac 3, Mac 2, Mac 1, Mac 2, or Mac 3 only. It will not get all the packets because whenever the switch which is connected to the line physical Mac, so switch will only switch the packets which are destined for these three MAC addresses only, right?
Yes.
So it will not push all the packets which are needed to go to all the.
Yeah. So there is a, okay, so let me draw. So this is a physical machine, this is a physical machine, and if this is a physical port, PETH1, PETH2, which is connected to a hardware switch, and if this is a port and this is a port, so this is a wire, right? Then everything on this wire has to have a forwarding table here which says which MAC address should go on this port, say 1. So for all packets that come to this switch physically from anywhere in the world, we'll have to match some forwarding table rule in that switch. And you are right, most of them in this switched hierarchy tree will always be Mac 1, Mac 2, Mac 3, Mac 4. So a packet which is destined to this PM will probably never show up on this port. Right? As long as it's a shared bus, that's a bigger problem. But in a switch tree kind of an environment, you will only get packets in your whatever branch.
And in the switch table for one interface, we will have three entries now.
3 entries, yes. Mac 1, Mac 2, Mac 3, Mac 4, all of them. Yes.
So basically, the Mac one that you were referring to would be either of these Mac 2, 3 or 4, right?
No. So now what's going to happen in this scenario, right? In this scenario, we have Mac 1, Mac 2, Mac 3, Mac 4. So any packet that falls out of this NIC can have Mac 1, Mac 2, or Mac 3 as the source address. Or any packet that's coming in can have Mac 1, Mac 2, Mac 3 as the destination address. Because this is all layer 2 switching, right? Now we have, in layer 2 switching, we have landed up in the same network. Now all we can use is the MAC addresses to distinguish our destination.
But why are we using Mac 1? Anyways, it could be either one of the Mac 2 or Mac 3. It should be either one of them. It goes inside one of the. Okay. So if we want to interact with.
Yeah, so if the host itself wants to use its own network.
That would be for Mac 1.
Yeah, that would be Mac 1. Yeah, so in fact, I've abused that a bit. I've said that if the host itself wants to use it, will get its own virtualized interface called E80, which will be called Mac 4. Right? So maybe it's Mac 4, not Mac 1. But it may need its own, it may want to do its own communication. Right? So for example, many VMs expose their dashboards over the network as a service. So you don't have to log in physically to that. You don't have to be sitting on that server to start VMs. You can start them remotely. So if you want to start and control VMs remotely, they have to be done on the network. And the network endpoint should lie on the host for the host service to run. Right? So for that it may need its own MAC address. Okay? I want to show a last design. I was going to talk a few things, but maybe I will at least draw a picture for it. And so this is the third design. We are out of time actually, so let me just draw this. This is basically hardware assisted IO. And here the multiplexing and the sharing and the setup is hardware assisted. By the way, one of the points that I didn't make is that both the approaches, the full and para, irrespective of the interface, because they are emulating devices, they can actually be supporting many more devices than actually available either physically, right, or they can take resources remotely and supplement the number of devices that can. So inherently the virtualization is also supporting what I am labeling as multiplexing, sharing, right. So like we are scheduling the CPU, we have to partition memory and we have to either partition or over provision device. In case of IO, the additional advantage is you can go outside the machine as well. In memory also you can go outside the machine and fetch memory from somewhere else. So you can say, your P2M mapping is no longer local. Your P2M mapping is actually on the network. You can do that, but the problem there is you will get hit with latency which is much higher compared to traditional memory access latency. Because IO latencies are already large and IO already operates in this network mode, because in bare metal also you may have an NFS which is anyway on the network, right. So the amortization of cost with IO is much more manageable than in memory. Okay. So I'm not going to say anything, I'm going to just draw a picture. And if you are late, you can leave. I'll probably draw this picture once again next time. I want to just leave you with this picture to say what's really the deal with what's happening in hardware assisted modes. And again, I'm going to do this with a NIC. So in hardware assisted mode, the only difference, or the one big difference, is that the hardware itself is broken down into distinct devices. So this is an example of one physical network supporting three different what are called hardware queues, or three different virtual network devices. And each of these virtual network devices can then be exported as a network device into the VM. Right? And then of course you need a driver which drives that virtual device, but now it's no longer virtual in the sense that it's no longer virtual as a software device. It's virtual, but it's a actual physical device. Right? And enabling of this breaking up of one physical device into multiple real virtual devices is what is called the hardware assisted mode of IO, where hardware is actually making more chunks of a physical. So eventually all that multiplexing and software devices of virtual devices we had to do because everyone wanted a device. So now if you have many small devices, we can give each of these small physical devices to every VM. Right? So all the MAC multiplexing, switching that we were talking about is actually now done in hardware. Right? So this is a hardware based partitioning and mux, demux, multiplexing and demux. Right? And that's the hardware assisted IO approach, where now hardware breaks up and supports newer devices, and these newer devices that can be now be connected to VMs.
Now your network card can receive only that particular MAC address.
Yeah.
You don't need to receive all MAC addresses.
No. So here also that has to happen, but that's happening in hardware. It will see multiple MAC addresses.
But now it has to receive only those MAC addresses, not all.
No. It only has to see the MAC addresses of the interfaces that it creates. Yeah.
Now the Cs2s can directly write to the register of the controller, right?
The register can write directly to the
Cs2s can directly write to the control register of the device.
controller. There is no controller. Control register. No. That will go through standard virtualization. Yeah. You can't still write directly to a control register.
But now we have three virtual devices which are assigned to three different virtual machines, right?
Yeah, so we will, I'll talk about that, what that is. So that's really the data channel. The control channel still goes to the hypervisor. But I'll say that, I'll probably add that details next time. Right? Okay, we'll stop here. We are already out of time.